All right, here's today's do now. Complete this on any blank do now space from any previous week. The graph of the function f above consists of 5 line segments. Let g be the function given by g of x is the integral from -3 to x f of t dt. Find g of 2, g prime of 2, g double prime of 2. Find the x-coordinate of each point of inflection of the graph of g on the open interval -3 to 7, and justify your answer. And then on what interval is g increasing? Pause the video, give it a try, compare your answers with each other. If you need a tiebreaker, message me and I can tell you what's what. All right, so the focus of today's lesson is integration by U-substitution, and this is part 2 of our lesson that we began on Friday. On Friday, we discussed the need for alternate methods of integration when fundamental theorem of calculus fails. And we specifically talked about situations where we had composite functions, that is, a function inside of another function. In these cases, we decided that there was a method called U-substitution which could be applied. And the objective was to take this complex composite situation and turn it into this integration of U. We then could apply fundamental theorem of calculus. We're essentially going to do the same thing today, but we're going to look at some definite integrals. And so the process has a slight twist to it. Let's take a look at our first example. Example 1. It says this: find the integral from 1 to 3 of x squared plus 1 cubed times x dx. First thing we ask ourselves is, does U-substitution apply? We notice here that there is in fact a function inside another function. We see that x squared plus 1, this quadratic function, is inside this x cubed function. So we're going to let that be our u. Now, following the same steps as last week, we differentiate u with respect to x. The derivative of u with respect to x is, in this case, the derivative of x squared plus 1, which is 2x. Algebraically manipulating this expression, this becomes du is 2x dx. Now, looking at our expression here on example 1, we see that we have an x dx, but this expression here is a 2x dx. So we can move the 2 out of the way by dividing it on both sides, leaving us with 1/2 du is x dx. Noting here that this expression has x dx and x squared plus 1, which will turn to u, and our expression has x dx, which will then turn into half du. Using these substitutions, we're going to rewrite our problem as the integral of u cubed du, and then that 1/2 will just come out front. Now, here's where the difference occurs from Friday. Because we have bounds, and because we are changing our variable from x to u, we must also change our bounds. Our bound that was 1 in terms of x is now going to become 1 squared plus 1. So now it will be in terms of u. And our upper bound, which was 3 in terms of x, becomes 3 squared plus 1. Okay, now following our fundamental theorem of calculus, we take our antiderivative for u cubed, which is 1/4 u to the 4th. And then our lower bound, 2, and our upper bound is 10. 1 squared plus 1 is 2, and 3 squared is 9 plus 1 is 10. This becomes 1/8 u to the 4th from 2 to 10. Now we evaluate. So we have 1/8 times 10 to the 4th minus 1/8 times 2 to the 4th. Or equivalently, 10,000/8 minus 16/8, or 9,984/8, or when reduced, 1,248. Pause the video if you need time to write it down. All right, let's take a look at example 2. All right, so same idea. First thing is, let's identify if there's a function inside a function. We notice here that we do have this 3 minus 5x inside of this 1 over x squared function. So we're going to let that be u. Then we're going to take its derivative. So du dx is the derivative of 3 minus 5x, or in this case, -5. Now, our expression here only has a dx. So when moving the dx to the other side, we get du is -5 dx, but we only want dx. So we'll divide both sides by -5. leaving us with -1/5 du is dx. We notice here the 3 minus 5x will become u, and the dx will become the -1/5 du. Okay, going ahead and substituting, we get -1/5 1 over u squared du, and then our lower bound becomes, now in terms of u, 3 minus 5 times 1, and our upper bound, 3 minus 5 times 2. Now taking our antiderivative for 1 over u squared, we note that 1 over u squared is u to the -2nd power. So this goes up a degree to u to the -1st power, and then divide by -1. So this is -1, 1 over u, from -2 to -7. The -1/5 and -1 cancel each other out, leaving us with 1/5 times 1 over u from -2 to -7. Now, let's evaluate. So we get 1/5 times 1 over -7 minus 1/5 times 1 over -2, which becomes -1 over 35 plus 1 over 10. Creating a common denominator, we get -10 over 350 plus 35 over 350, or 25 350ths. And then after reducing, we get 1 over 14. Okay, pause the video to take your notes, and then go ahead and do Math 9 and verify that what we've done makes sense. All right, our last example. Example 3. The integral from 1 to e natural log of x over x dx. Okay, now our inside function here may not feel as obvious. There's only two functions in this picture. There's natural log, and then there's 1 over x. The first thing I would do is identify which of the functions that you have would have a derivative that is the other, right? So if I did 1 over x and I took its derivative, I would not be able to eliminate this natural log x. But if I took the natural log of x and took its derivative, I would be able to eliminate the 1 over x. So that means that natural log x has to be our u. We're going to go ahead and take its derivative, and we get du dx is 1 over x, or du is 1 over x dx. So we have our u will become ln, and then that 1 over x dx is going to become du. So we'll rewrite this, changing our lower and upper bound based on u. So the lower bound becomes natural log of 1, and the upper bound becomes natural log of e. Noting natural log of 1 is 0, and natural log of e is 1. The antiderivative for u is 1/2 u squared. Now we are from 0 to 1. So this is 1/2 1 squared minus 1/2 0 squared, or just 1/2. All right, pause the video if you need to, then go ahead and knock out this homework set. Feel free to message me with questions.